what we're going to be looking at is force. And a related subject to force is mass. Okay? So where do we start? Well, whenever you don't know where to start, you go back in time and you start with the Greeks. When you start with the Greeks, you probably start with a guy who did the most analysis of all these subjects from physics, right? That was Aristotle. And just to clarify, Aristotle probably did not write everything he's credited with. Remember, he was a Macedonian, and he was Alexander the Great's tutor. Okay, he educated Alexander the Great. So when Alex became the boss, Aristotle was sent to Athens, or he went there. I think he was sent there, and a lot of Athenians considered Aristotle a spy. Like, this guy's going to be telling Alex something about us, and so they were very reserved with Aristotle. But Aristotle founds his school, and a lot of the Athenian rich kids, right, they went to that school. And they took notes when Aristotle gave his classes, his lectures. And so I think that a lot of what came out of the Aristotle school were simply stuff that his students also wrote. So I think it's a collection of Greek thought, you could say, in those days. So I don't think it's like Aristotle had all this time in the world to just sit down and write. He was giving lectures, he was talking, he was doing some politics out there as well. And I think a lot of what we have today, which is credited to Aristotle, really comes from his students. Okay, just something, again, food for thought. Okay, anyways, we go to Aristotle. What did he have to say? And for this, we have to start with, again, what Aristotle said about force and mass, or his notions about motion. Okay, and here we have it. This is out of his book, Physics. His book, I think, or his student's book, says all movement is either compulsory or according to nature. And if there is compulsory movement, there must also be natural, for compulsory movement is contrary to nature. Okay, so he had this notion that there's these different kinds of movement. One where it's natural movement, and the other one compulsory. Something moves something else. Okay, so this was Aristo's notion of this. And he had this notion that a lot of people, a lot of generations later, criticized about him, which is his notion that if you drop two stones, the heavier one will fall faster. And these are notes that you get from his book, that you can see where his train of thought goes. He says, everything that is in motion must be moved by something. In other words, he thought that you required a force to constantly move something. Okay? And then he says, if a given force move a given weight a certain distance in a certain time, and half the distance in half the time, okay, half the motive power will move half the weight the same distance in the same time. This was his reasoning. And he was criticized a lot for this, for this train of thought by later generations, because they said, I don't think that's true. Okay, and here, let me give you another one related to that one. It goes like this. It says, for let B, well, let's go simply with the circled one there. It says, then air is twice as thin, the body will traverse B in twice the time that it does D, and the time G will be twice the time E. And always by so much as the medium is more incorporeal and less resistant and more easily divided, the faster will be the movement. Okay, so he had these notions about something that moves twice as fast as something else, and that was related to the weight and to the force applied. And he was studying motion, or trying to analyze motion in these terms. Okay, so this is more or less his train of thought. And again, he was criticized quite a bit by later generations who said, the problem with you, Harry, you did not do any experiments. See, if you would have done an experiment and observed, you wouldn't have said such nonsense. Okay, and that's where they introduced, especially in the 17th century and onwards, that you need experiments and you need to measure. You need to come up with an equation in order to say things like, in order not to make these big blunders. And the answer is no. You don't need measurement, you do not need equations, and you do not need to do experiments. What you need in science is to explain. At home, you can do all the experiments you want, you can measure all you want, you can calculate anything you want, bring all the equations you want. So far you have a description. So far you have nothing but a description. Science is not about describing, science is about explaining. When you come to the conference, we want an explanation of the mechanism, not a description. And so the fact that you do an experiment, the fact that they overruled Aristotle and said, you didn't do an experiment, and because of that you did not observe. If you would have observed, if you would have measured, you would have calculated, you would have had the equation, then you could have said something a little more sound. And yeah, that's only for descriptions. So far, you have nothing more than a description. Okay, science, explanation, not descriptions. Okay, here we have Galileo, who comes in the 17th century, and he's made famous because people say, oh, you know what Galileo did? He proved Aristotle wrong. He proved Aristotle wrong. Okay, how did he prove him wrong? Well, he dropped two balls from the Tower of Pisa, right, in Italy, and he found out that they both fall at the same time, even though one was heavier than the other. Okay, and here is more or less Galileo's argument on that. That's from his book, okay? And he says the following. He says, he remembers a dialogue. It was common to make books in those terms in those days. And he's got Salviati speaking. He says, Aristotle says that an iron ball of 100 pounds falling from a height of 100 cubits reaches the ground before a 1 pound ball that has fallen a single cubit. I say that they arrive at the same time, okay? And he says, Aristotle declares that bodies of different weights in the same medium travel with speeds which are proportional to their weights. Okay? And then he says, you will have to show that a stone of 20 pounds moves 10 times as rapidly as one of 2. But I claim that this is false, and that if they fall from a height of 50 or 100 cubits, they will reach the earth at the same moment. Okay, this was his argument. And this is more or less what Galileo had in mind. Okay, here you see it. Give me a second here. Okay, there it goes. There's a good old Galileo there. And he's allegedly went to the Tower of Pisa. Okay. Dropped the stones. He shows that it's, they fall at different speeds at different levels. And did Galileo ever perform this experiment? That's the question we have. Okay. And all I can say is, I think it's apocryphal. I think he did not ever perform that experiment, especially from Tower of Pisa. I think he just rolled balls on inclined planes, and he studied that because he was able to measure them with clocks. Okay, and so he had different inclined planes. He had different weights, balls of different weights, and he just rolled them and figured out, measured and found out that they don't match what Aristotle said. That was essentially his idea. But the first question we have to answer is, because a lot of people just repeat that and say, oh, Galileo, he was such a saint. Was Galileo, is he the guy who discovered this? Is he the guy who went to the Tower of Pisa and threw two balls from there, or, two stones or whatever? Is he the guy who did all this? Or the first guy? And so let's first settle that, because if you repeat that, all you're doing is making a fool of yourself. Okay, means you didn't do a minimum of research. Okay, so let's get that out of the way first of all. Okay, here we have a fellow who did it in 1586. Remember, Galileo started doing these experiments, the original experiments. He did them around 1604, and he writes his book in 1638 after the Catholic Church put him under house arrest. He wasn't allowed to publish things related to God and how the planets move. But he was able to do his experiments en masse. Again, he took up his old experiments from 1604. He took them up again close to 1638. He started doing these experiments again, and then he writes his book, 1638. Here's 1586, 50 years earlier. Okay, this is Mr. Steven. He's Dutch, and he says the following. This he writes in his book, The Elements of the Art of Weighing. Okay, he says, the experience against Aristotle is the following. Let us take, as the very learned Mr. Cornets de Groot, most industrious investigator of the secrets of nature, and myself have done. 2 spheres of lead, the one 10 times larger and heavier than the other, and drop them together from a height of 30 feet onto a board or something on which they give a perceptible sound. Then it will be found that the lighter will not be 10 times longer on its way than the heavier, but that they fall together onto the board so simultaneously that their sounds seem to be one and the same rap. Okay, that's 1586. Was Mr. Steven the first one? Well, for this we have to go back 10 years, and we find this fellow. His name is Giuseppe Moletti. Okay, and he already in his book. This is in 1576, 10 years earlier, when Galileo was still in high school, I guess. And he says the same. He says more or less, he said, let fall from the top of a tall tower 2 balls. One of 20 pounds of lead and the other of 1 pound. Okay? And then he says at the end, he says, they touch the earth or ground at the same moment in time. Now, whether Moletti did this or not, I can't tell you. What I can tell you for a fact is the following. Moletti was professor at the University of Padua in Italy. When he retired, Galileo took his job. They knew each other. They were friends. Moletti came before Galileo. He wrote books before Galileo, and he was Galileo's teacher. So what do you think Galileo got this two-stone deal, this two-balls deal? He probably got it from Moletti, more than likely. Now, where did Moletti get it? Was he the first guy? Did he get it from Stevin, or did Stevin get it from Moletti? Well, we go back in time, and this is important so that you don't make a fool of yourself every time you say, oh, Galileo proved. Let's find out, okay? Here we have this fellow. His name is Cardano, and he wrote this book in 1550 where he says the same thing when he analyzed already the weights of things falling, okay? Was he the first guy? You can see what the subject matter of his book, a lot to do with religion, but he did try to analyze, the nature of things, okay? In fact, he calls his book The Subtlety of Things. Okay, was he the first guy? Well, let's find out. Here we have a few years earlier, like 13 years earlier. This is Nicola Tartaglia. He writes a book in 1537 where he drops objects from a window all the way to the bottom. He already had determined that, that objects do not fall at the same time. At different times, as Galileo had said. And you say, okay, so I guess Tartaglia gets the Nobel Prize. He was the first guy. Well, someone preceded him by at least 1,000 years. Okay, and here's we have Mr. John Philoponus. Okay, let me get back in here. And he said already in the 6th century. Okay, he says the following. He says, "For if you let fall from the same height 2 weights, okay, one many times heavier than the other, you will see that the ratio of the times required for the motion does not depend on the weights, but that the difference in time is very small." So he did not measure. He could not come up with an equation. He could not tell you how fast or slow because they didn't have, what do they have, water clocks in those days? They didn't have accurate clocks. So he wouldn't be able to tell you exactly how they fell. But what he could tell you is that, look, Aristotle is wrong. Something that weighs 10 times as much as another one doesn't fall 10 times as fast. Okay, so this has been going on for years, but everybody gives credit to Galileo. And Galileo took a lot of these things from someone else. Why did Galileo become famous? For 2 reasons. Maybe you could say 3. One, he did experiments. Carefully constructed experiments. Then he measured with a clock. And third, it was Newton who made Galileo famous. Newton was the guy who said, oh, Galileo, he came up with this, and he built on what Galileo had already, set the foundations for. Okay, that's why Galileo's famous today. Did Newton read Stevin? Did he read Tartaglia? He probably didn't even know that these guys existed or even wrote books. I don't know if Newton knew any of these other fellows. Otherwise, he wouldn't have credited Galileo with so much. It's like, you built on the nearest guy to you. Galileo died on the year that Newton was born. And so, it's like this is a book that's available to him. That's what he uses as a foundation for his theory. But he didn't go through history to find out, everybody who came up with the two-ball thing and who talked about mass and force and so on. But, think about something else. The Arabs in the 10th and 11th century, they were in their golden age. And they were doing a lot of experiments, optics especially, and they probably figured a lot of these things out as well. I don't have access to all these Arab books, but I'm sure if we go through their books, we're going to find a lot of information regarding force and mass as well in those books. I'm sure they discovered that Aristotle wasn't quite right in his mind. Okay, so here's just a summary, of all the people who preceded Galileo, not all of them, but there you see some names. You see Philoponus, Tartaglia, another fellow there, Benedetti, all these guys, Moletti, Stevin, all these people preceded Galileo in the two-stone or two-ball experiment, They probably didn't have accurate clocks to measure, but they pretty much realized that, there is no difference, or very little difference at best, if you threw 2 stones with different weights, to the ground. But one thing that Galileo did was he enunciated essentially Newton's first law. That one's credited to Newton. Did Newton come up with that one? And here you see what I'm talking about. Aristotle said that an object requires continual force to keep it moving. Galileo said an object moves forever unless, something kind of retains it. And I'm sure Aristotle figured that out as well, But the issue is, look at how Galileo has it in his mind. He says, an object continues moving in a straight line unless a force acts upon it. That's his notion. What do we get from Newton? Well, we get the same thing. It's known as Newton's first law of motion. Okay, and here you see it. Okay, his first law of motion. And already you had people like Pierre Gassendi, who 1 year before Newton was born, 1641, already wrote about it. Okay, and Newton just rephrased that, and he gets the credit for it as the first law of motion. Oh, Newton came up with it. No, he did not come up with it. But Newton rephrased it. He says, everybody perseveres in its state of being at rest, or of moving uniformly straight forward, except insofar as it is compelled to change its state by forces impressed. So Newton just rephrased what all these people already had in mind. It's not like Newton invented the first law of motion, but he's given credit for it, just like Galileo is given credit for the two-ball experiment. Okay, so you got to keep in mind that unless you do a little bit of research on some of these issues, you're giving credit to the wrong guy, and all you're doing is repeating what they taught you in school. You got to be careful with that, because there is information out there where you can show that these people were not the originators of those theories. If you leave it up to the mathematical physicists, they will tell you the only two people that existed that were alive in the 17th century were Galileo and Newton. And that's not true. There were a lot of people there in those days, and a lot of mathematicians who were very well versed in mathematics and so on. Okay, so, and they also, provided theories and so on. There was a lot of discussion. Newton wrote to Leibniz and vice versa, mathematician in Germany. These guys had correspondence between them. They exchanged ideas, not through the internet, but, it was by mule. But they did exchange information. Okay, so, who can be credited with what? That's up for grabs sometimes. All you can do is go off the record and not by, hearsay, word of mouth. So how about Newton's second law? Okay, second law of motion, force equals mass times acceleration. Did Newton come up with that? Well, all I can tell you here is that Newton did not come up with this notion, let me put it over here, of mass times acceleration. Force equals mass times acceleration. You won't find it in his book. It's not in there. Okay? What Newton said, essentially, a change in motion is proportional to the motive force impressed and takes place along the straight line in which that force is impressed. And from that, the Frenchmen who got a hold of his book said, force equals mass times acceleration. It wasn't Newton who came up with that equation, but that's essentially what he insinuated, and that's what we learned today. We say, Newton's second law. Okay? How about gravity? I mean, Newton's famous for gravity, right? Let's find out what Newton proposed on gravity. And here you see it. Okay? This is what he wrote in Principia, two places, in section 12 and section 13. He essentially was doing theorems. He was trying to prove certain things. Okay, so he says, I say that a corpuscle put in a place outside the surface of the sphere is attracted to the center of the sphere by a force inversely proportional to the square of its distance from the same center. And then, because that was for spherical bodies, he said something similar for non-spherical bodies. He says, if the attraction of a body by another shall be far greater when it is attracted in contact than when the bodies may be separated by the smallest distance from each other, then the forces of the attracting particles in the distant parts of the attracting body decrease in a ratio greater than the square of the distances from the particles. So he essentially came up with this square of the distance rule, okay? But it turns out that you have his countryman, Robert Hooke. And when Newton writes his book, Principia, Robert Hooke accused him of plagiarizing Hooke's ideas. Because Hooke was in charge of the Royal Society, and he wrote many letters back and forth with Newton. And he says he proposed to Newton the square of the distance. And he maintained that position until the end of his life. And Newton said, I never credited Hooke for that specific thing, because Hooke did not come up with an equation. He had he did not prove it. He just guessed at it. He had a hunch that it was true. Whereas Newton was able to show in his book that it was true. That it was exactly the case. And so it was a difference between one guy believing it and the other guy proving it, so to speak. And so Newton said, I'm not going to give credit to Hooke, even if he did mention that to me, okay, because Hooke never proved it. And there were other people who also talked about the square of the distance before Newton. The only thing Newton gave there is this mathematical certitude, where he says it is true. Okay, so essentially he proved it through these theorems that he wrote in his book. Okay, so just keep in mind that how things really develop. Not everyone who is credited with having discovered something was the actual discoverer. There was someone who preceded him who came up with the idea, and this guy just developed it further and fine-tuned it. And Newton is credited primarily for mathematizing it. And that's more or less what he also credited Galileo with. He said, unlike all these other fellows who said the same thing, Galileo mathematized it or proved it, kind of put it in rational terms, so to speak. Okay, so that's where the difference is. It's not like Galileo came up with these ideas or Newton came up with these ideas. These ideas were already on the books. Okay, but what Newton did not discover was the following. One of the things, okay, there's a couple. This is the first one. He didn't discover that his force equals mass times acceleration, if we're going to give him credit for that, had to do with push, and his gravitational equation, force equals gravitational constant g, mass 1, mass 2 divided by distance squared, that's pull, okay? And the other thing here is that these two are different. The first formula is not equal to the second formula, which mathematicians today, they make them as equal, and they say, okay, mass times acceleration is equal to whatever's on the right-hand side of that on the pull equation. Not true, okay? It's not true. Not qualitatively true. What's the difference? Okay, let's find out. That acceleration in the push equation, in Newton's second law, that acceleration includes distance traveled. That's not distance of physics, that's the distance of mathematics, and it's distance traveled, displacement. Position, because position is also a pair of numbers, okay, ordered pair. The distance in the pull equation, that is separation between two objects, between mass 1 and mass 2. So the distance in the pull equation is not the same as the distance traveled in the push equation. Okay, that's the first thing we need to note. And Newton never discovered that. And again, he did not discover that one equation or one notion that he put forth had to do with push and that the other one had to do with pull. Okay, is that the only thing he did not discover? No, there was something more fundamental that Newton did not discover. Okay, and that's this, that you need an object to do physics. You can't do physics with concepts. Okay, and this is very important. And here you see he writes to Richard Bentley, fellow who looked up to him because he was such a great mathematician. And he writes to him in 1693, he says, that gravity should act without the mediation of anything else is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. Newton could not explain why an object is attracted to another gravitationally, why the earth is attracted to the sun, why the moon is attracted to the earth. He could describe and tell you the relation, the mathematical relation, square of the distance, but he could not tell you why. What was causing gravity? And there he essentially confesses that he has no clue whatsoever. Why? Because he did math and he did not do physics. He was a mathematician, not a physicist. Okay? And unfortunately, what we have today is a branch that came out of Newton and Galileo and went into mathematical physics, and they keep doing equations, they keep doing physical interpretations using concepts like mass and force and field, instead of using objects, physical objects. And here you see from Mr. Galileo what the issue is, okay? And he says the following, he writes this, he says, natural philosophy is written in that great book whichever is before our eyes, I mean the universe. But we cannot understand it if we do not first learn the language and grasp the symbols in which it is written. The book is written in what? Mathematical language. Okay, this is what Galileo proposed, and that's what Newton liked, and that's where we are today. We have this mathematical language, okay? And the symbols are triangles, circles, and other geometrical figures. Absolutely not. We do physics with objects, not with triangles, okay? But this is what these people had in mind. They wanted to prove things geometrically, mathematically, without whose help it is impossible to comprehend a single word of it, without which one wanders in vain through a dark labyrinth. We're still wandering through a dark labyrinth. Why? Because these people think that it's a question of using math, and math has nothing to do with science. Neither do experiments. You can do all the experiments you want in your lab. You can do all the math you want. You can calculate whatever you want. That doesn't mean you're going to be able to explain how Mother Nature does the mechanism. That's where the problem is. And today we have a lot of math and a lot of equations, a lot of measurements. What don't we have? We don't have an explanation from these people on how the universe works, which is what the ordinary person out there thinks is physics and wants the mathematician to explain to him. People want to know why this pencil, my famous experiment, okay, why this pencil falls to the floor and not to the sky. Why does it always fall downwards? Let me do it again. Repeatable, there he goes. Let go of it, falls always to the floor. Why? What causes it to fall downwards, not upwards? And they can tell you how fast it goes. You have Newton's equation. You have the gravitational constant. You have the calculation of the gravity here on Earth. All this stuff we have. Those are descriptions, mathematical descriptions. We still don't have an idea, mathematicians don't have an idea, what causes this pencil to fall always to the ground. All they have is description, mathematical descriptions. And there you see, mathematics is the language in which God has written the universe. No, absolutely not. The way Mother Nature, God, the devil, all these fellows, right, Father Universe, the way they run the universe is with objects, with physical objects. Some of them we cannot see or touch. Others we can see or touch, okay, and touch. But some we cannot. And that's what these people never figured out. You can't do an experiment to figure out gravity. You can't do an experiment to figure out gravity because there's nothing to see and nothing to touch. So you can go to the lab and do all the experiments you want on gravity. That doesn't mean you're going to come up with the explanation. You're going to come up with a description, a mathematical description of how fast or what the acceleration is. You can get all that stuff. But what you will never be able to figure out through math or through experiments is how Mother Nature does that trick. For that, you have to make assumptions. Some people make assumptions that there are particles pushing the pencil downwards. Other people say, well, you remove the air between the pencil and the floor. When you remove that, well, then there's a push force, again, that pushes them together. Maybe the earth upwards or the pencil downwards. Or maybe it's waves pushing the pencil downwards. Or maybe it's ropes pulling it from the ground. Those are assumptions. You have to make an assumption in order to give a physical interpretation. Okay? And math cannot help you at all for that. At all. Okay? All you have with math is descriptions. Okay, here's a fellow. His name is Kevin Brown, and he has the math pages. And he tells you essentially what the issues were in the 17th century and where we are today. He does a pretty good summary, so please bear with me, and you'll learn something from this fellow. Okay, he says the following. He says, René Descartes proposed a mechanistic approach to physics. Okay, all causal influence is transmitted by direct contact between material entities. René thought that you needed physical objects to produce interaction. Gravity, right? Like Aristotle, he rejected the idea of vacuum. René did not believe in the vacuum. Okay, we disagree there, but okay, this is his assumption. He did not believe that there is nothing out there. It's all something. Okay, the ether, believing that there can be no space without substance. Okay, this is René Descartes' notion. Galileo, the cause of the acceleration of natural motion, and this is from Galileo, these items, he writes this. He says, this is what people today think, and maybe it's premature to think of that we can figure out how Mother Nature does these things. And he says, he summarizes, he said, this is what the theorists of today think. This is in Galileo's time. We're talking about 1630s, 1640s, okay? He says, some explaining it by attraction to the center, by whatever, okay? Because again, you're not explaining, all you're doing is describing. If you cannot tell me what's pulling it to the center or pushing it to the center, you have not given me an explanation. So he's wrong in saying explaining it as that. He can say, yeah, we notice that everything falls to the center of the earth, but we don't know why. So he doesn't have an explanation, he's got a description. And people confuse those two. He says, others to repulsion between the very small parts of the body. Okay, these were different theories going around in those days. Galileo summarizes those. And while still others attribute it to a certain stress in the surrounding medium, which closes in behind the falling body and drives it from one of its positions to another. Okay, so we have this push gravity. That's what all these people were essentially suggesting, push gravity. Some people have resuscitated push gravity these days. One fellow had a long discussion with Mr. Van Flandern, Tom Van Flandern, died a few years ago, and he was a push gravity guy. Okay, and this fellow, Kevin Brown, he continues, he says, he talks about Newton here. He says, every two particles of matter are compelled toward each other with a force directly proportional to their masses and inversely as the square of the distance between them. This universal gravitation was apparently contrary to the mechanistic precepts of Descartes because it implied that widely separated bodies exert forces on each other directly without explicit reference to any intervening substance. Okay, so this was the issue. Was there a substance? Was there a material thing between two objects being attracted gravitationally? Newton disavowed the notion of direct action at a distance because he could not see or touch what was between two objects, okay, especially two celestial objects. Newton's overall approach was that nature consists of atoms moving according to abstract mathematical laws in an empty void. That's a mathematical description, not an explanation. What was Newton? A mathematician. He gave us descriptions. He did not give us explanation. And gravity might be a primary attribute of matter with no material intervening mechanism. That was his notion. In other words, the physical explanation he had no clue about. He only had a mathematical description. Okay? Well, we continue here with this fellow's analysis, math pages. And here are the other people who more or less tried to bring them together, Newton with Descartes. Here we have Huygens, Leibniz, and Bernoulli. And they sought some way of reconciling Newtonian gravity with a mechanical philosophy of Descartes. They sought an explanation of universal gravitation in terms of direct contact between what? Material entities. Because they said, how does Mother Nature do this? We need to have attraction between two objects. There's got to be some material entity that brings them together. There can't be any action at a distance without some intervening object. That's what they were saying. And they tried to do this, but they couldn't see or touch whatever was between the objects. So it's a tendency for bodies to be drawn together is inherently problematic in the context of Cartesian physics because contact forces are, by definition, directed outward from the surfaces of bodies. Even if we hypothesize bodies with hooks or other interconnecting shapes, we must still rely on a force of cohesion to maintain the shapes of the bodies. So we haven't avoided the need for a primitive force of attraction. This shows that purely material mechanisms, in the sense of Descartes, are inherently inadequate to fully account for the phenomena of experience, meaning primarily gravity. And yeah, see, this is the issue that we still have today. Because they cannot see, because they cannot touch whatever physical object is between, say, the earth and the sun, or between the moon and the earth, they say there's nothing there because an object is that which you can see or touch. And no, you're not going to be able to see or touch the mediators Mother Nature uses to do light, gravity, or magnetism. She made them invisible. She made them intangible. We're not going to elucidate them. We're not going to reach an understanding of them through equations. We're going to reach them only by, taking a couple beers and visualizing, proposing, making assumptions. That's the only way you're going to figure this out. Okay? So, all these experiments all these people run are worthless to tell us how Mother Nature runs her shop. They're not going to be able to figure out what's in that invisible, intangible world of hers. Okay, so this is essentially what we have here. This was his ending in the math pages. Kevin Brown says, nevertheless, there were many attempts to give a mechanistic account of gravity in terms of contact interactions between what? Material bodies. You want to have a mechanistic interpretation because otherwise you're not doing physics. That's the issue. These attempts tacitly rely on unexplained primitive attractive forces to maintain the shapes and configurations of those bodies. These attempts usually took inertia for granted as a primitive attribute of matter. They started including this inertia, mass concepts, mathematical concepts. That's when they invented these and started working with these concepts instead of working with objects. Why? Because they couldn't see or touch the mediators. The same people in other contexts sought to account for inertia in purely relational terms by invoking primitive interactions between what? Material objects. You have to fall back on material objects. And these people, on the one hand, they had this duality, where on the one hand, they would talk about inertia, mass, force, concepts, maybe energy. And then on the other, they try to simulate them with objects. And you can't put the two together. You either work with objects and say, Mother Nature does this with objects, or you start working with all these mathematical concepts, and then, without noticing, you turn them into physical objects, you reify these abstractions, turn them into physical objects, and now you say, oh, the force, oh, the energy, mass, moved this way, weight went upwards. So this is where they got into trouble, because they started using all these concepts and turning them into physical objects. And they thought that by doing so, they were giving you a physical interpretation. And today they have this duality again. They say, we explained it. Did you really explain it? Well, we describe it, and science is about describing. So is it about describing or about explaining? And that's where the problem is. These people don't explain. And only when someone puts them against the wall and starts pummeling them, they say, well, no, we haven't explained it. But that's philosophy anyways, because we don't know what's in that invisible world anyways. That's their answer. Okay, so what happens? It turns out that Newton's ghost followed all the way to the 20th century to Mr. Einstein, who tried to figure out or found out this principle of equivalence. Okay, but Newton was there right behind him because Newton said, "Hey, you're going to give us a description, a mathematical description. How about an explanation?" And you can see here what Einstein goes in there and just does a description. He says the following. See if I can get it on the other side here. Give me a second. It says, this is Einstein speaking here. Okay, it says, a little reflection will show that the law of the equality of the inertial and gravitational mass is equivalent to the assertion that the acceleration imparted to a body by a gravitational field is a physical object, but see, a field is imparting acceleration. Okay, listen to the words. To a body by a gravitational field is independent of the nature of the body. Okay. For Newton's equation of motion in a gravitational field, written out in full, it is what? Inertial mass times acceleration is equal intensity of the gravitational field times gravitational mass. And he continues, it is only when there is numerical equality between the inertial and gravitational mass that the acceleration is independent of the nature of the body. Okay, and Einstein never figured out either, like Newton didn't, that one has to do with pull. Force equals mass times acceleration is push, and gravitational one is pull. And so they never figured out that one has to do with push, the other one with pull. These are two qualitative different notions of force, first of all. Second, as I already mentioned, and I'll go with that in more detail in the future. I've done it in the past, but I'm going to do it one more time. And that's the acceleration. In the second law, Newton's second law, force equals mass times acceleration, the distance there is not distance. It's distance traveled. It's motion. Whereas the distance in the gravitational equation is the true distance of physics, separation between what? Two masses, two objects. Okay, so these are different. They're not the same equation. In fact, the second one is not even force. It's tension. It's known as tension, not force. But Newton didn't know that either. Neither do the mathematicians. Okay, so what do we have? How do we explain Einstein's principle of equivalence? Under the rope model, it's a no-brainer. It's a no-brainer. Qualitatively, we can explain it very easily. We have one hydrogen atom. It doesn't matter to what that hydrogen atom belongs. It could belong to a feather. It could belong to an elephant. Here I put it as part of an elephant. And here you can see where the two equations, Newton's two equations, if we give it to Newton, right, fit in. Okay, here it is. In one case, you have pull. Okay, and that atom there is being pulled by all the ropes that it's connected to, which means to every atom on Earth. I didn't draw them all, by the way, okay? Some people say, hey, you drew only 10 ropes there. No, we got gazillions of ropes tied to that single atom that belongs to an elephant. So it doesn't matter at that distance, at that exact separation between that atom and the center of the Earth or whatever. It doesn't matter if that atom is going outwards, being pushed, or being drawn towards the Earth. At that distance, at that specific separation from the Earth, that atom is equal, that the two equations are equal. They're equal why? They're equal because of what Einstein just said. You know, for a single entity, like in this case this atom, at a given distance, it's got the same number of ropes converging on it, whether it's going outwards or coming in. That's the principle. That's the reason behind the principle of equivalence. Something Einstein wasn't able to figure out. Why? Because he did math. He did not do physics. None of these people do physics. They all came out of this notion that Galileo set out there, that the language of the universe is math, and you got to do experiments and observe and to figure out things. And it turns out, you know, you can do all the experiments you want, you'll never figure out gravity because there's nothing to see and nothing to touch. You can see the things that you can see and touch, but you cannot see the things that you can't see or touch. And so, what are you going to do? I mean, here you have the pencil. Okay, do you see anything there? You see anything here? Is there anything you can touch here or here? And if you go out and you say, well, there's air. Yeah, air. But air is not producing gravity. So there's nothing you can see or touch. And so what experiment are you going to do? Are you going to take me to the lab and say, I'm going to show you gravity. Let me show you the gravity. What are you going to show me? All you can do is make an assumption. And whatever here is here, and whatever's here is invisible and intangible. So don't ask, what does it look like? Where is it or whatever? You can't see or touch it. You can only make an assumption and say, let us assume that all atoms from this pencil are attached to the Earth. Then you can explain gravity. Okay, now you can explain why this falls downwards and not upwards, because you don't have ropes coming from up here, you have ropes coming from down here. Very simple. Okay, baby stuff, kindergarten stuff. Okay, once you have an explanation, right? Once you make the right assumption. Okay, one fellow asks, he says the following in relation to this. He says, what is the rope made of? And I thought it was very clear. It's made of two threads, twine threads. We're done. I mean, I don't know. Go to the hardware store tomorrow and ask for a rope, two-strand rope. And you'll find out that that rope is made of two strands. We're done. See how simple it was? What is a rope made of? Two strands, two threads, whatever you want to call them. Two wires, two cables, whatever you want to call them. Two strings. Okay? Very simple. Another fellow says, okay, smart Alec, let's find out. What is the thread made of? Well, he says, what are the threads made of? Well, there are no threads. There is a thread. There's a single thread. Okay? And this thread makes up all the ropes and all the atoms in the universe. So this is the underlying assumption. We're saying there's a single thread in all of space. But what he's asking is an irrational question. Okay, it's an irrational question. You say, why is it irrational? Okay, let's find out. Yeah, we find out why that question, what is the thread made of? We're talking about a single thread, okay? Why it's an irrational question. Here it is. It's an irrational question. Why? The thread is an elementary or fundamental entity. What is an elementary entity? It's one which is not made of parts. Okay, the thread is made of a single piece. It's the single thread hypothesis. So what happens? You take, for example, quantum mechanics, and they have also what is known as an elementary or fundamental particle. And you say, well, what is an elementary or fundamental particle? Well, it's a particle that's not made of simpler parts. Very simple. And so now the reporter at the end of the room says, what is it made of? Well, it's an irrational question because by definition, an elementary particle is one that is not made of anything. It's made of a single piece. And the guy is asking, what is a single piece particle made of? Well, it's not made of anything. It's made of a single piece. But that's not what the quantum mechanics answer. What the so-called theorists answer, they say, give us more money and we'll build a collider that has is as big as the orbit of Pluto. Then we can smash this fundamental elementary particle and we can tell you what it's made of. And then, so A is made of bees. And so now the reporter comes next year and he says, well, what are the bees made of? And the guy says, give us more money, we'll build a collider as big as the galaxy, and we'll tell you we'll smash these particles and we'll tell you what it's made of. And so this is the problem because they define the particle as an elementary fundamental particle. And when you ask them, what is it made of? The guy says, give me money and I'll tell you. That's not how we do it in science. In science, we say the thread is made of a single piece. It's not made of parts. It's a fundamental elementary entity. The buck stops there. We don't say that the thread is made of threads, of particles of this, of that. Thread is made of a single piece. It's the ultimate entity that makes up everything else. Hopefully, that's the rational universe. If you keep saying, well, is that made of parts? Is it made of particles? Can it be stretched? If you go with that, then now you got opened up a can of worms because now people are going to say, well, what is the particle that makes the thread made of? Well, let me get you a collider as big as the universe, and I'll tell you. It's like that. No, you have to stop somewhere. You have to start with some foundation. The foundation is the thread is the ultimate hypothesis. Period. We're done there. It doesn't go beyond that. It's an assumption. It's an assumption to be able to explain atoms and ropes, and from there we can explain light, gravity, and the workings of the atom, etc. That's the way it works in science. It's only in irrational people, religious folk typically, that they say, well, what is this made of? What is that made of? And it's made of the thing, once you tell them that A is made of B, they say, well, what is B made of? And what is C made of? What is D made of? And so on down the line. It never stops with them. Okay, and so this is where the problem is. It's an irrational line of questioning and thinking.